Yeah, strength of the dominant.
Yes. So this talk is follow-up to Jakob's talk about something he said there. And while I'm here, let me also just say that we have some money for a postdoc position in Prague in the second half of this year, but for a short time, 3 or 4 months, which is going to be the European Union citizens. So if anybody's interested or knows someone who's interested, please let me know. Yeah, so this is joint work with Leszek Kołodziejczyk, and it's about Jakob's proof system that he very carefully avoids naming when he talks about it. Well, we call it the dominance proof system in this paper. And I want to show that it's hard in extended resolution, that it's as hard as this system G1, which has some reasoning with QBFs. So his system is sort of complicated. So I will start by describing a streamlined version of it. So this is, and this is going to be very similar to a talk I gave in Berkeley last year. So I might have heard it before. So a proof system. So it's going to be extended Frege plus this rule. So extended Frege means we can derive some formulas, and suppose we get to some formula gamma. So the rule is, if we have a formula gamma in variables x, and if we also have, firstly, delta, which is a set of extension axioms, defining new variables z from x. I'm calling this system extended Frege, but actually it's extended resolution, but I want to make things easier for myself. So I'm thinking of it as a bit stronger, but these are extension axioms. So this just says that z1 is x1 and x2 and things like this defining the z's. Or you can think of it as a circuit defining the z's from the active. 2, omega, which is a Hertz substitution mapping x variables to variables from x together with z, or maybe to literals. And 3, an extended Frege proof that any assignment satisfying gamma and delta also satisfies gamma where we change the variables by this restriction substitution, and this thing right this one. So gamma and gamma after restriction, and x after the restriction is lexicographically less than x before the restriction. Under these conditions, then gamma is unsatisfiable. So a refutation in the system is going to be, we start with some formula, we do various extended Frege stuff, we derive some gamma, and then if you can show these 3 things exist, then you can conclude that it's unsatisfiable and that your original formula was unsatisfiable. And just to be clear what this is, So this is x is some variables, x1 up to xn, so we can think of it as a string. We compare strings in the lexicographic ordering. This is x, which maybe is some assignment. This is x after the restriction, which is going to be some different assignment. So we're saying that if you apply omega, things satisfying this, you get something satisfying this, which is smaller. So this should remind you of Jakob's system. And in particular, he had this division of things you write down into core constraints and derived constraints. And gamma is the core constraint. In particular, here it's the thing we're refuting. And delta stands for the derived constraint. So this is some kind of auxiliary thing that helps us refute gamma, but which we don't really care about. So yes, and Jakob's proof is done over cutting planes and so on. But by the time you have these redundancy and extension rules, it's really the same thing as just starting an extended Frege. So I guess you can still read that.
But we should think of this as like, this is a one-shot thing. I just do
Yes,
one
just
extended Frege until I'm ready and then boom.
Yes. You could make this into a rule, you can apply more than once, but actually you just need to do it once. So I guess certainly you should think that this system can be simulated by Jakob's system. You have the cutting planes to do the resolution stuff, the extension rules, and you have the dominance rule, which is basically this.
I'm a bit confused. When you take lexicographic ordering,
Yeah.
do you order x variables only or x and z variables?
X variables only.
But x restricted to omega, it will contain z variables.
Well, yes. So we have a formula, we have n x variables, and so we have a formula with 2n positions for the variables for doing lexicographic ordering of n-bit strings.
Yeah.
And then this is saying we make the substitution in one side.
Yes, but your substitution will create z variables. How do you compare them if you say that you don't use them in your ordering?
You're doing the Lex order on the domain variables from X, right?
Yeah.
Right.
You substitute and you get something with z variables.
Well, think about what this is saying about the assignments to X. If you have some assignment to X, this says that if you apply this, if you have some assignment to X and Z.
You're not mapping X union Z to X? And the other
Well, I'm mapping variables here,
He means that on z it's probably identical or not.
but this just means the lexicographic ordering
Yeah.
after the substitution.
But after the substitution, you are not in the domain of your ordering. You said that you order only x variables.
Well, okay, I take it back that I order only X variables. Maybe it's not helpful to say that. So
You're taking the X variables ordered and looking at their values and then looking at their values under omega.
which sends them to Z
It might
variables.
become z variables.
Yes.
That's okay.
well, let me give
just
the
say that
proof
no
of
matter what
bounds
z
to
values
this.
are.
It might make more sense.
Yeah.
So how do you prove this is sound? Because the strength of the system will turn on how much you need to do to prove it's sound. So proof of soundness. So I want to show that if you have this thing, then gamma can't be unsatisfiable. So we'll assume for contradiction that gamma is satisfiable, and in fact we'll say let alpha be the least, meaning lexicographically least, assignment to x variables such that it satisfies gamma. So we can get this assuming that gamma is satisfiable. And then we use these things delta. We extend alpha union beta, such that this thing satisfies delta. So what does this look like? And this might explain a bit more what's going on here. So we can draw the variables like this. It's slots for values. So this is the x variables and this is the z variables. And we start with some assignment alpha here. And then we use delta, which is just extension variables. So just using a circuit, essentially, you can get values beta here. And then omega is a map from X variables to both kinds of variables. And we'll use that next to pull back this assignment to here. So we'll say, well, so one thing is we have from the provability condition at the bottom that this thing, alpha together with beta, satisfies this, the right-hand side of this entailment. And what does it mean? It means if we define alpha prime to be this whole thing pulled back onto X variables, it means that this new alpha prime is less than the original alpha. So kind of working inside the slot of X variables, we've made a new thing and we compare them in the ordering and it's got smaller. So let me rewrite that. So we let alpha prime be the composition of this new assignment with the omega. Sorry, that's omega. And then we have alpha prime satisfies gamma from this. And alpha prime is lexicographically less than alpha from this. And this contradicts our choice of alpha as a lexicographically least. So this is the same as Jakob's proof of soundness, I guess, done in one step rather than iteratively. So is everyone happy this is a sound rule?
I think I agree with Alexandra that I want you to order everything in the range of your substitution, but other than that, I'm super happy.
Okay, but if you want to order all variables, you can do it. You just put the Z somewhere at the end of the ordering, so they don't affect anything.
The target of the substitution should be relevant. So if there are any of these text variables, then the lexicographic order is simple comparing two and bit strings.
Are you agreeing or disagreeing with me?
I'm agreeing with you and disagreeing with the fact that there should be a problem.
Yeah, so two things to observe about this. What's happening with this delta and omega? So delta is more or less an arbitrary circuit which takes these values and gives you values there. And then omega does something, but what it can do is it can just take whichever values it wants here and pull them back to here. So if you have any polynomial time function on n-bit strings, you can put it into this kind of picture. It could be what this thing is doing in the soundness proof. And let's also observe that, well, let me go on to the next thing, which is that what kind of system do you need to prove this is sound? So sound arithmetic, what do you need? So what you need is, the difficult thing really is the leastness here, because we have this rather large set of assignments that satisfy gamma, and we want to take the lexicographically least thing in this set. So this can be done in T12, and I want to convince you it can't be done in S12. But we're talking about G1, so let me say what G1 is, and actually I might run out of time. So here are some proof systems. So at the bottom we can have resolution, and cutting planes, which is what Jakob was using, and maybe AC0 Frege here. And then I'm writing this down as examples of relatively weak systems. Frege and extended Frege. And if you really want to go higher, you can with these systems, G systems of quantified Boolean formulas. So there's G1, there's G2, and so on. And what are these things? So F, which actually we call G0, can be characterized as the propositional sequence calculus. So proofs in the propositional sequence calculus is a sequence. So you keep deriving a sequence which looks like this. You have some propositional formulas on the left and an arrow and some propositional formulas on the right. And if you can derive that some formula F actually, if you can derive a sequent of this form, it means you've refuted F. So sequent calculus derivations look like this using just propositional formulas. And then I won't write it, but these systems G1 and G2 and so on, this is if you allow QBFs here. So if you have existential propositional quantifiers or universal propositional quantifiers, but no alternations, so everything is kind of sigma Q1 or pi Q1, and you have this kind of system, then that's G1. And G2 is having some alternations and so on. And so in particular, G1 refutation is going to look like a sequent derivation in the system from some axioms that ends up showing that F entails contradiction. And we'll have some quantifiers in the body of the proof, but we're just interested in refuting CNFs actually, or formal propositional formulas. So this will be quantifier free. So the quantifiers appear in the proof, but we're refuting something quantifier free. And we also have, say, that some other structure here. So say EF is like tree-like G1, and G1 is tree-like O2, and so on. So the reason these systems were introduced is that extended Frege is the same as extended, well, it's the same as PV in some sense. This is if you're doing propositional reasoning here, it's the same as doing first order reasoning here. And there's some issues that here things are non-uniform, here they're uniform, and I'm going to ignore questions about uniformity. So this is polynomial time stuff, and then here is T12, and this is T22. So these theories were introduced such that the proofs with quantifiers in these systems match exactly, are a way of modeling the induction on formulas with quantifiers in these systems. So what is the connection between PV and extended Frege? It's that
Is the G Gensen?
I don't know. What does the G stand for? Okay.
Next letter after E.
Next letter.
No, maybe Gensen is stronger than even extended Frege.
Yeah.
It seems like a value judgment.
So we have this characterization that ignoring the uniformity stuff, if PV proves that some universal sentence like this proves something is false universally, that's true if and only if we have a short, which I guess I'll just, all proofs I'm talking about are short. We have a short extended refutation of the Frege refutation of the translation of this. So this is meant to be a polynomial time formula, a PV formula. And this, the whole thing is then called a for all pi B1 sentence. And more or less, sentences of this form provable here correspond to short proofs in extended Frege, where the thing being refuted here is a kind of natural propositional translation of the claim. So this is polynomial time, so it's like a circuit. This is you take the circuit, the first order variables, the Boolean variables, and you compute what the circuit does. So you can put it into the propositional world, then you can more or less put it back. So this is the way in which these things are like this. And in general, the correspondence is really on, well, the one I want to talk about is on the provable formulas with no quantifiers, which are going to correspond to these. So I'm really talking about the pi B1 consequences of these theories, at least in my mind in this picture. And there's this known result due to Sambas and Young-Krajcek about T12. Well, first of all, what is T12? So T12 can be characterized as PV together with the least number principle. So you can take this as an axiom scheme saying any non-empty polynomial time set has a least element and T12. Now, if you're only interested in the low complexity consequences of T12, such as these consequences, then you actually don't need the full strength of this scheme. You just need PV together with an axiom that says every PLS problem has a solution. And really, this is a kind of local version of the least number principle. So a PLS problem is a triple of some element T, a domain D, and a neighborhood function N. And you can draw these. So you have some set of binary strings, which I'll draw as an ordering from the bottom to the top. You have some set D, maybe in a couple of blobs. And you have an element T, which is in D. And you have this N, which is meant to go downwards and stay inside D. And so if you can find a point where N takes you outside of D, where N doesn't give you a least element inside D, that's a kind of local minimum of D under N. And the PLS, the axiom here says that in this situation, there always is some local minimum in this sense. So yeah, I guess I should go back to saying that the least number principle is what you need to prove the soundness here, because you need to prove there's a least thing in this large set. So T12 and thus G1 prove the soundness of this, so it simulates Jakob's system. And for the other direction, you can kind of observe that it actually, the thing you actually need looks more like this, because this function n, taking you to a smaller solution, is kind of like this operation here, taking you to a smaller thing. And well, so let me show that. How much time do I have? 5 minutes. Oh, okay. So let me just rather informally say, so this is the description of T12. It's PV plus something. So logically, on the propositional side, it should be extended Frege plus something like every PLS problem has a solution. So how do we say PLS problems have a solution in extended Frege? So I will complete the proof. So suppose G1 proves something is false. Something is a contradiction. Then there is a PLS problem such that extended Frege proves, so this I guess is informally, that if this thing is true, then the PLS problem has no solution. So this is more or less the contrapositive of my statement that this is like EF plus PLS. So what does this look like? So in EF, we can do the following. We start with, well, we have a proof of, we start with this, and then we can derive that something is in the domain. So we're proving there's a PLS problem in the solution with no solution. So there should be a non-empty domain with something in it. And there should be, the neighbor is always below the current thing in the domain. So what does that other condition look like? So in EF, we can also prove that with this PLS problem, if you have something in the domain, and you define a new thing to be the neighbor of the thing in the domain, then the new thing is in the domain, and it's lexicographically smaller than the other thing. So this is just saying if phi of y is true, then D is non-empty, and it has no local minimum under this neighborhood function n. And now you should look at this, and look at this, and see that in this system, you can now finish the proof. And so you've simulated G. Because this thing here is just gamma. This is delta. So this is defining new variables Z just by circuits from the old variables X. This is gamma under omega. So what is omega? So we have to give some substitution, but we just let omega just replace xi with zi. So in this picture, well, I'm simplifying things a bit, but in this picture, the Z is kind of just has more or less the same structure as the X's. And omega is just copying the things we want back into here.
So is this like next states the transition really? The description of the next states in the transition?
Let me just finish the thing. And then this is the same as X. Omega is less than X. Yeah, so this shows that by this rule, we can conclude that this is unsatisfiable, therefore phi is unsatisfiable, therefore we refuted phi in our version of Jakob's system. So, sorry, what was the question?
So, I mean, so I normally think of the N as kind of a next state pointer.
Yes.
And so like Z then becomes, or Z becomes the next, the thing you pointed to as opposed to some, yeah.
I don't know what you would gain by talking about states in this case. So I mean, I'm thinking of the PLS solution as being a local thing rather than really trying to simulate it, but that's maybe not what you mean.
Well, I mean, there's in this graph, okay, so you've got a graph without degree 1 in PLS, right? And so I was just the vertex or state. So X is a description of a vertex and Z is a description of the vertex pointed to by in this picture.
Yes, I mean, the vertices are just the space is really the space of assignments. So it's just binary strings we're going through. Anyway, that's the end of my talk. So I finished the proof. So.
Just to make so I got confused about this Lex order. I mean, the point is that it doesn't have a domain, right? It's just talking about bit strings.
It's just a formula with.
It's just saying that I have 2 bit strings on this fixed length and sorted in Lex order, the following claim hold, and you code it in some appropriate way.
So I wanted to say, I wanted to say it privately, but now I will do it publicly. So you said that you don't apply more complicated substitutions. You do. That's what you do. So you simply look at Z variables as the function in X, they compute and you make the substitution.
Yeah, it's disguised.
Yes.
In our system, we don't do this. This would be like, you would literally have, it's very precise. It's one linear inequality with just an exponential sum.
It's the same.
Yeah, that's what I'm saying. Yes.
You have these derived constraints. And you use them to smuggle in more complicated operations.
Yeah, no, you can totally, with the extent with delta, you can totally do this. Yes.
Have the derived constraints. This is just extended Frege.
No, you're absolutely right that we can, through the back door, we can do very sophisticated substitutions. But you have to do it through the back door.
I understand that, but.
No, it will be very important to, sometimes for complicated things, I will carefully build up a circuit that given X says that I'd like to have this very, very complicated substitution. And once I've set this up, you just boom, do this, but it's look very innocuous. I'm just replacing X by Z, right? But the circuit, then there's a circuit somewhere. Typically, that's in the derived set. I have a circuit that computes this very complicated.
But then my objection completely disappears, or because if you do any clever or complicated substitution on variables, then it will give you whatever dual pullback on assignments. Then it all disappears.
Okay, you might be on the same page.
Yeah, you're on the same page. So let's do it.
So good thing, speaking again. Yeah, in the last talk of the workshop, gonna be given by Marco Tomasino. Do you use the Blackboard?
Yes, I'm using the Blackboard.
I think this is where we're only doing very simple substitution. But nobody stops you from building up a very complicated circuit that you will have to evaluate in order to.
That's why you extend it very now.
Although again, even without this backdoor, you don't need any backdoor. Safety, and also you won't need a backdoor. Then you. So the rule is powerful even with vanilla substitution without any circuits hidden